let's talk about finding areas. And here's an example. Find the area enclosed by y equals to x squared and y equals to x plus 2. Now to help you to understand what's going on, let's draw the graph. Everyone knows here that y equals to x squared is this graph, right? Y equals x plus 2 would be y-intercept 2 with slope of 1. So here's 1, 2. That's like that. And now you can see clearly where the enclosed region is. This is your region, right? We also need to know where they meet. So how do you find out where they intersect? Yes? Make them equal to each other. And then you have x squared minus x minus 2 equals to 0. So you can factor it, right? And this is 0 when x is 2. And this is 0 when x is negative 1. And it's in accordance with our picture, so it makes sense. Okay, now to find the area, I want to suggest two methods. But only one of them is the one that I want you to try. Okay? The second method will be there just to give you some support of why the first method does work. And here's a big idea that we will be using very frequently, not just in this class, but also in Calc 3 and also in Physics 2. Okay? If you take Physics 2, you end up doing this a lot, which is that any physical quantity is the sum of its parts. Okay, and then this will be in different contexts. In physics, sometimes you want to find the mass of something, and you say it's an integral of small masses. Sometimes you might have an electric field, and you have to add up all the small electric fields. You've seen that? E is equal to integral of dA in that class, right? Yeah. So it's something it's a truism. It's always true. If you take something and divide it into small pieces and then add them up, you recover the original thing, right? So it's just a truism, and it doesn't seem to say anything, but this actually is how we use integrals in most of the contexts. So it's so important. Anything is sum of its parts. However, this dA is somewhat ambiguous because this dA depends on how you chop the thing into small pieces. So here's what we're going to do. We're going to take this area and we're going to divide this into very thin strips. Okay? And if it's so thin that the width is so small, then here's what we get. So our dA will look like this. Our dA would be like a strip. I drew it rather big, but it's supposed to be very, very thin. So it's a very small increase in the x direction. Guess what this is called? It's called dx, right? dx is an infinitesimal increase in x, right? And then now we have to figure out the height. Well, the top graph is x plus 2. The bottom graph is x squared. So if you take the difference between the two values, so the y value on the top is x plus 2. Y value on the bottom is y equals x squared, right? So if you take the difference between the two values, you end up with the height, right? So that's what we're going to do. We're going to say that this length here is really top minus bottom, where the top graph is x plus 2, and the bottom is x squared. Now we have the formula for dA, which is dA is base times height, or height times base. Height is x plus 2 minus x squared. And the base length is dx. Okay. Oh, but then you have dx, right? Dx means that you have to know where the x coordinate begins and where it ends. What should I put here and there?
-1 and 2.
-1 and 2. Okay. that's what you have to do. Now let's find the antiderivative. X integrates to 1/2 x squared. 2 integrates to 2x. X squared integrates to x cubed times 1/3. And then you have to plug in 2 and -1. Okay, and then 2 squared times 1/2, that's 2. 2 times 2 would be 4. 2 cubed is 8. 8 over 3 is what you have here. Sorry, I'm moving a little fast because I'm running out of time. -1 squared is +1, so you get +1/2. -1 times 2 would be -2. -1 cubed will be -1, but there's another negative, so it'll be +1/3. Now, that was something that anybody here can do, but here's like the common source of mistake, this parenthesis. Don't ever forget this parenthesis. You're doing this plugged in, the two things are subtracted, so this parenthesis is very important. People mess up the answer. After getting all this right, they mess up the final answer just because they forgot this parenthesis, okay? So don't ever do that. All right, so if you continue on, 2 plus 4 is 6, and then minus 2, so it's 8. -8 over 3 minus 1/3 would be -3. 8 minus 3 would be 10. 10 minus 1/2 will end up being 9 over 2. Okay. Another something that you can just calculate, right? All right, so that's method 1. You found the area like that, but you might not be so confident of your answer. So let me give you another second method. So I'll give you second method, method 2. And this one works like this. You think of this area that we're trying to find, this one, as like you have, no, not that one. Oh, we can put a dotted line here. Minus like that. Right? You agree with this?
Yeah.
Right. This piece will be taking this piece and getting rid of this piece. Then you're going to get that, right? The reason I like these two is because this is really the area under the curve. Isn't that right? And what did we learn about area under the curve? It's that definite integrals. So this is x plus 2. So if we integrate x plus 2 from -1 to 2 dx, you get this area under the graph. Minus, if you integrate from -1 to 2 of this graph, what is this graph though? X squared, right? That will be same as this area in question. But now look at this. They have the same interval, right? So you can actually combine this into a single integral, which is -1 to 2 of x plus 2 minus x squared dx. And what do you know? This is exactly the integral that we did here. It's the same thing, isn't it? It's the exact same integral. So, of course, it's going to, again, give you 9 over 2. So that's the second method. Now, however, this is just for verification. I really want you to be able to solve it in this way, because this captures the basic idea that we'll be revisiting over and over again. Now, let me just point out one more thing. This is also a graph, right? And if we use the fact that the definite integral gives you the area under the graph and draw this and see what happens, you'll see that it's hard to see, but it's a parabola that's like this. Okay. And it's what that integral is doing is the area under this parabola, green line from -1 to 2. And you might be asking, like, why is this area here that looks totally different from the other ones, same thing as this area? You can make a good argument for that by thinking of the following. Think of this area as like sticks, made of sticks. Like hard chopstick, wooden chopsticks, like they're very, very thin, or toothpicks if you want, okay? Toothpicks of different length. Then the area of these toothpicks will add up to the entire thing, right? But then, imagine that these toothpicks are supported by another set of toothpicks that looks like this, right? So that's why they're retaining this shape. So there's something that's supporting them. But then you take it away. What happens? They're all going to fall down to the bottom, right? And if they fall down, the shape these toothpicks will give you will be this one. Because look, what's the length of the toothpick here? At the far left end. What's the length? 0, right? And then it becomes the longest here, and it becomes 0, right? So you see that it's 0 here and 0 there, and at some point here it is the longest. You get exactly that shape, right? So that's another way to think about this. Okay, so in general, this is true. General formula is area between fx and gx over the interval a to b, so that the picture is fx here, and here's g of x, and here's the interval a to b, is given by area equals the integral from a to b of f of x minus g of x dx, provided fx is above gx. So fx is above gx, just like the picture, right? You don't want to do gx minus fx, then it'll be negative, right? On this interval. Now, rather than writing it this way, I really want you to think of this formula as area is equal to a to b, top minus bottom, dx. So that's the formula.